Okay, hi guys. Happy Friday afternoon to you all as well. Can you guys see me and hear me okay? Awesome, thank you. All right. So hopefully you guys all felt pretty good about that quiz. Thank you guys for all coming back to our Zoom room for the second half of today's lecture. Today what I'm gonna do is use the rest of class today to finish up some of the topics of stereochemistry that we did not get to prior to the quiz. And then of course, we're not on the quiz. And then I don't think I'm gonna have time quite to set the stage for chapter 6, but if I do, I do. And if I don't, then we'll dive into chapter 6 on Monday after I set the stage. So with that said, there's really only 2 topics that are left over from the rest of chapter 5, and those are the topics I'm going to touch on today. So first, we're going to talk about the chiral compounds without chiral centers. These are special cases and special circumstances. And in order to do that, we will also just remind everybody that we already know about the special case of conformationally mobile systems. So this slide should look familiar to you guys. You've seen it before. We talked about how lucky we are earlier this week that for chair forms, because those chair forms can relate to each other by just bond rotation, we don't actually have to consider the chirality of each individual chair form. What we can do when we're looking at chirality is instead look at the most symmetrical conformer, which turns out to be the flat representation like I have drawn out here. So when we're trying to figure out if a cyclic molecule, a cyclohexane-based molecule is chiral or not, rather than looking at the chair form where you might make the mistake of seeing a mirror image that is not superimposable, these two are, although they are mirror images of each other, right? They are also superimposable because they are in equilibrium with each other, because of the bond rotations that are happening. And so that means we can essentially take the average planar configuration, or the most symmetrical version of how we could draw this, to check for that internal plane of symmetry. And indeed, even though our chair form here looks like it could be enantiomeric with its mirror image, the mirror image is actually the same. And so what we have here is a meso compound, right, where we have an internal plane of symmetry. So in this case, we're talking about how rotation around bonds and kind of the average or the most symmetrical version of the conformer gives us insight into whether that molecule is chiral or achiral. It turns out that there are a couple of special cases where you can have a molecule that has no chiral center at all, but because of a particular geometric constraint imposed on the structure, it can have chirality. So there's just a very few examples of these, but they're really interesting. So I wanted to make sure to bring them up and show them to you guys. The first type of these is called allenes. Allene is the specific name for this type of structure where you have 2 double bonds directly next to each other that are sharing the same center carbon. So this type of an arrangement has a very specific consequence on the stereochemistry of these compounds. And you can see from these allenes that they have mirror images, but because we know that we cannot rotate around double bonds, we can see that because there's not rotation, these mirror images are not superimposable on each other. So these 2 molecules that I'm showing you here are actually enantiomers, even though there's not a single chiral center in this molecule. So let's think about how this works. First of all, think about just for a second what the hybridization of the central carbon atom is. And if it helps you to think about the hybridization of these 2 sort of external carbon atoms first, go ahead and do that. And then look at this internal carbon atom of the allene. Think about what that hybridization is. So somebody pop it in the chat box. What do you think the hybridization of that central carbon atom is? It's attached to just 2 things, right? So it has just 2 groups attached. So it is an sp hybridized carbon atom. Because it's an sp hybridized carbon atom, that means that there are left over 2 p orbitals that are not hybridized. One of those p orbitals is going to be in the plane of this page. The other p orbital is going to be perpendicular to the screen here, coming forwards and backwards from the plane of the screen. So what that means also is that if we look at the double bond on the left here, and we see that the sigma framework is perpendicular to the screen, where this H bond is coming out towards us, this methyl group is going back behind us. That means that the remaining p orbital on this carbon is vertical and in the plane of the screen. And so that p orbital is pairing with the p orbital on the central carbon that is vertical and in the plane of the screen. And so it is occupying that p orbital. The remaining p orbital that is horizontal, perpendicular to the screen, is available to participate in a pi bond still on the other side. And indeed, that's what's going on. So you can see in this carbon on the right, the sigma framework here is in the plane of the screen. And so the remaining p orbital here is coming out at you and going back behind the screen and participating in a pi bond, where the pi bond on the right-hand side of this particular enantiomer, that hot dog bond, is on both sides of the screen, whereas the hot dog bond in the left-hand pi bond is in the screen above and below the sigma bond we can see. So you can kind of see how that means, because we know we can't rotate around these, that we have forced ourselves into a conformation where the 4 different substituents on the ends of this allene are pointed in a particular arrangement, right? And so these cannot be superimposed on each other. Make sense? Cool. All right, so let's see another type of molecule that has this problem, or I don't know if it's a problem or not, but has this kind of special case to it where, because of restricted rotational capabilities, the molecule itself becomes chiral, even though there might not be a chiral center. So the second example looks like this, and it's a whole family of what's called biphenyl derivatives. So this aromatic ring is also known as a phenyl ring. When we connect it to another aromatic ring, it's called a biphenyl. And they're connected via a sigma bond. So normally, if all of these groups that are halogens here were just hydrogen atoms, that sigma bond could have rotation around it. And so you would have that free rotation, and this would not be a chiral molecule. However, because these groups are pointed towards each other, and they're constrained in that geometry by the shape of all of these sp2 hybridized carbons of this ring, these substituents here make it impossible to do that rotation because of steric hindrance. They would run into each other. So what you can imagine then is if you have two phenyl rings that are like this, they cannot rotate around freely because the groups that are sticking out here would bump into each other. And so these systems are similar to the allenes in that they, because of a restriction of their rotation, they can be chiral, even though there is not a chiral center in the molecule. So this has to do with what we'll call conformationally locked. It cannot rotate around the sigma bond, even though normally you could rotate around the sigma bond. In this case, the steric's prevent it. And so these conformations, the far left and the far right here, are in fact enantiomers of each other. They are non-superimposable mirror images, and so they fit that definition of enantiomers. These are pretty rare cases, so I'm bringing them up to kind of complete the chapter. Don't expect there to be a ton of questions on these 2 examples. There might be one question that comes up on these. So, all right, the next topic that I want to cover today is called Fisher projections. And these Fisher projections are a different way of representing a molecule, especially with respect to stereochemistry. So we know a lot of different ways to represent chemical structures, and sometimes it's easy to forget that these aren't actually the structures. They are just representations of the structures. But think for yourself for a minute about what the different types are that you know that we know, right? So some of them are Lewis dot structures. right? We also know line angle drawings. And we also know kind of an extension of line angle drawings called perspective drawings, where now we can use the wedge and the dash to show three-dimensionality on top of our line angle drawings. All of these are useful. There's another topic or another type of representing chemical structures that is very useful for a very narrow type of molecule. But because it is something you will come across in organic chemistry, I want to make sure to show it to you so you guys understand and know what it means. This is not my preferred way for people to draw or even think about molecules, because it really is limited once you get to more complex molecules. But in terms of being complete, I need to make sure you guys see this. Okay, so in a Fisher projection, the goal of a Fisher projection is to be able to write out a version of a molecule without having to use wedges and dashes, but that still contains all of the information of those stereochemical centers. So what do I mean by that? Let's look at an example, because that's really the best way to do it. So say we have a chiral carbon here. We're used to thinking about these and looking at them in a way where two bonds are in the plane, one bond is a wedge coming towards you, the other bond is a dash going away from you. But you can actually also look at it if you view it kind of from an angle, so that two bonds are coming towards you in a horizontal way. That would put two bonds going behind you in a kind of vertical way. And so you can see, if you imagine looking at this bond, at this molecule from this angle, then the carbons labeled 1, 2, 3 would be vertical in a line and going straight back 1, 2, 3. And then the groups right here that are kind of coming out at you from the direction you're looking would show up like bow ties, right? And so this is part of the definition of a Fisher projection, is that you want to arrange your molecule so you are looking at it from a direction where the horizontal lines coming towards you are the bonds that are coming towards you are along a horizontal portion of the molecule, and the bonds that are going away from you are going back behind the plane, that they'll be in a vertical line. And then the Fisher definition says that we can flatten this out so that we don't have to draw the wedges and dashes anymore. But if we call this a Fisher projection as it is flat, then every chemist will know, just the same way every chemist knows that a wedge bond means that this OH group is coming out of the page at you. If I call this a Fisher projection, that means that these two are coming towards you in a bow tie fashion, and these vertical ones are going away from you in the dashes. So it's a very strange way to look at these molecules. It is a historical way, I will say. It's a little bit arcane. It's from before the days of graphic design, and when it was easy to draw things like this in publishable papers. It's harder to draw a single line than it is to draw a wedge or a dash if you're trying to like publish a manuscript before the days of like computers, right? So it's a historical artifact, but because it's a historical artifact, it will come up now and again. It also turns out to be very useful for sugar chemistry. So things like glucose have 6 carbons in a row. And if you have the D versus the L glucose, most of those carbons have a hydrogen and a hydroxyl group. And which direction they point is what tells you whether you have a D glucose or an L glucose. Same thing with like other, there's a million types of sugar or carbohydrate molecules, the monomers that make up sucrose and all of the different things that are out there. This Fisher representation turns out to be very useful for them, because you can draw a whole line of carbons, and then which way the hydroxyl groups go can tell you which isomer you have. So a couple of other things to note about Fisher projections. Before I get to that, this is just a ball and stick version of what we just did, because sometimes it's a little bit easier to see. What we want to do here, the bonds to 1 and 2 are in the plane of the screen. What we want to do is orient ourselves so that no bonds are in the plane of the screen. And you can see now that the bonds 1 and 4 are coming towards you with bow tie wedges. 2 and 3 would be going back behind, and arrange them vertically because the bow ties have to be horizontal. And then when we flatten it out, this, if we call it a Fisher projection, then it contains the stereochemical information that is shown here. Okay, so some caveats about Fisher rules. So typically you want to keep if you have a long carbon chain, you want to keep the whole carbon chain in a vertical line. You ideally want to put your most oxidized carbon on the top. So that's what it sounds like. It's a carbon with as many oxygens as it can be. And those two are not that important for the purposes of this class, because I'm not really going to ask you to draw Fisher projections. I might ask you to convert a stereochemical version into a Fisher projection or vice versa. But if you have, these next two are very important. If you have a Fisher projection, then rotating that Fisher projection 180 degrees in the plane of the page that it's written in does not change the molecule at all. And you can see that here. If we convert our Fisher projection into our wedge and dash version, then we rotate it, and the things that were going forward are still going forward. The things that were going back are still going back, right? So 180 degree rotation is allowed because you still have the same molecule. However, if you try to rotate a Fisher projection 90 degrees, then what you happen is that your bow ties are suddenly vertical and your dashes are suddenly horizontal. And the stereochemical information associated with this molecule is not represented by this Fisher projection. This actually turns out to be the enantiomer. So if you rotate a Fisher projection by 90 degrees, you can imagine you're taking all of your bonds that were coming forward and flipping them to the back, and all of your ones that were going back and flipping them forward. You've just changed the stereochemistry. So you are not allowed to rotate your bonds by 90 degrees, or your molecules, by 90 degrees in a Fisher projection. Okay, I know those are kind of weird. Again, they are not going to be a focus of this class, but it's something that I needed to make sure you guys have seen for completeness sake, and because you will see it again sometimes. All right, I want to take just a moment to give some final words on the importance of stereochemistry. We've seen this flowchart a number of times now, or this organizational chart rather, and I want to point out I've actually hidden some Fisher projections in this chart the whole time. You guys, I guess, didn't realize that they were there, but down here on the bottom right, these are indeed Fisher projections. And so now you guys can actually see and redraw these if you want to in the bow tie version, and you'll be able to see that these indeed are diastereomers. But that's not really where I want to go with this. What I really want to go and kind of wrap up chapter 5 with is to kind of take a moment to say, well, we spent a couple of classes on this. You guys just took a quiz on it. Who the heck cares, right? Why does stereochemistry matter? So we talked already about these two enantiomers that have different smells. And we've talked about how different molecules can interact with your chiral enzymes, your taste receptors, your smell receptors, your biological enzymes, your metabolism enzymes in your body. But, this doesn't seem like that huge of a deal, right? So here is a huge deal. I don't know how many people have ever heard the story of thalidomide, but thalidomide is a drug that was given in a racemic fashion. And remember, racemic means a 50-50 mixture of the R and the S enantiomers. And it was a drug that was approved by the FDA and prescribed to pregnant women who were having morning sickness issues to treat their nausea. And one enantiomer of this racemic mixture causes birth defects. So it was administered as a racemic mixture, and then it turns out that one of these enantiomers causes birth defects. And obviously that's, tragic and terrible. But what it did was it made the scientific community, the medical community, the pharmaceutical community take stock and recognize that it is dangerous to not pay attention to stereochemistry, right? And so now when you have a drug that has a chiral center in it, or if you have a drug that has a stereoisomer, you have to either get approval for that drug as its pure stereoisomer, and have to have strict purity protocols and pay attention to levels of the other isomers present, or you have to go in and thoroughly characterize all of the biological activities and ramifications of the opposite stereochemistry and any other what would be considered sort of impurities to make sure that a situation like this doesn't happen. Well, what does that mean in a practical sense? Well, one, it means that we have safer drugs now, right? But the other thing it means in a practical sense is that there's a huge need, a massive need for chemists who can make molecules with the appropriate level of purity with respect to stereochemistry and the stereochemical configuration at particular centers. And so with that, I just want to say this thalidomide story is from decades ago. I mean, probably close to a century ago. And so, you know, this story might not seem that timely, but I want to point out that the Nobel Prizes have not come out for this year yet. They'll come out, you know, in the fall. But last year's Nobel Prize in chemistry was awarded to these two chemists who developed methods to create molecules in a chiral way. So they developed catalysts that, sorry, I lost my focus there for a second. These two scientists developed catalysts. They're called organocatalysts because they're not metal-based, which is environmentally friendly. But the key point here is that the catalysts can be used to create chiral molecules, right? So I pulled in a couple of details from the Nobel Prize press release. I've got a link down here for this where you can go and read more on your own. But it starts off right off the top. Building molecules is a difficult art. And that is true. Any molecule, whether it's chiral or not, is actually, synthesis is a very challenging endeavor, as you guys will see over the next chapters and over the next semester. So tools that chemists can use to help make synthesis easier are in high demand. And in particular, being able to construct molecules with chirality under consideration is really important. So I gave you the link here. I will post these slides on Canvas. I actually do post every slide set on Canvas after every lecture. So if you guys aren't seeing those slides, you want to make sure you're checking out the modules tab on Canvas. They're up for every single class. But just kind of take a moment and reflect on how neat it is that the 2021 Nobel Prize was about chirality of molecules, right? Pretty neat. So with that, I'm gonna let you guys go, and I am going to let you guys enjoy your weekend, and we will set the stage for chapter 6 on Monday, and then we'll get into chapter 6. Quiz grades should be available tomorrow, would be my guess. I saw that go by in the chat. All right, thank you guys. Have a great weekend.